Okay, so now we're beginning to talk about some known and useful random variables. And in specific, I'll be discussing the Bernoulli, uniform, binomial, and exponential. In this video, I'm discussing Bernoulli and binomial, and why I've grouped them together is because there is a relationship that exists between both of them. Okay, so let's begin. A Bernoulli random variable, as is stated here, is an indicator of whether an outcome is of one type or another. So it's the most simplest form of any random variable. For example, a coin toss. It can be a heads or a tails, right? Or maybe the example of the random walk. The person can take a right or a left. So they're just like two possible outcomes, right? And in order to denote that, we use this random variable and we call this Bernoulli random variable. And then obviously, because it's a random variable, it will have a distribution that will be referred to as the Bernoulli distribution. It is a discrete probability distribution of a random variable which takes a binary output. So instead of um, like h and t, for example, in heads and tails, I can express that in terms of 1 and 0. If the probability of getting 1, which is heads, is p, and then the probability of getting the other outcome, because there are only two outcomes possible, is going to be 1 minus p, right? The way we denote this random variable, let's say I'm using x again, is this. It can either get a 1 or a 0. If it gets a 1, the probability, or with probability p, and 0 with probability 1 minus p, right? So this is pretty simple, but things get a little interesting and a little complex when we consider or when we combine many Bernoulli random variables. For example, I can have x1, x2, and so on outcomes of n independent coin tosses. Sorry. So each outcome of the toss of a coin is a Bernoulli variable, right? So let me say I'm saying x1, x2. These are all Bernoulli, and by the way, these are also referred to as Bernoulli trials, right? So these are all independent Bernoulli trials. But what if I'm interested in this random variable, right? The sum of the success or maybe the failures of all of these, for example, right? So this x is not a Bernoulli random variable, right? So now let's see what this is. Okay. So the idea behind the distribution, the Bernoulli distribution that we just talked about, is that the experiment is repeated only once. Right? So as I said, what happens if we run more than one trial, right? And also assume that trials are independent amongst each other, right? What happens then? For example, I was talking about the flipping of a coin. That's the simplest Bernoulli trial, right? Let's modify the flipping of the coin multiple times, right? Instead of one time, let's say I'm flipping the coin 5 times, right? Let's flip a coin 5 times. Now what happens? Also, I have some assumptions. So I'm assuming that heads, if the coin shows up heads, this is a failure. So I'm actually representing heads as a failure and tails as a success, right? So because they're just two outcomes, I can always represent it in terms of failure and success. And each trial has like the total probability 1. So there are half chances of success, half chances of failure, right? This is a fair coin, right? So 1/2 probability of failure and 1/2 probability of success. And this goes back to a definition of Bernoulli when I said the probability of like one of the outcomes is p and the other outcome is the probability of the other outcome is 1 minus p because there are only two of them, right? Now this problem has become slightly bigger. Let's visualize just one scenario. Let's say I start tossing the coin and this is what I get. Right, so I start tossing a coin. I got heads, 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 all failures, and then success, success, right? Or maybe going back to the idea, to the definition of Bernoulli, 0, 0, 0, 1, 1, because I can represent this using zeros and ones as well. right? So again, repeating, every individual trial is a Bernoulli and its probability is either P or 1 minus P, right? So because the way I have sort of built this problem is that my heads is a failure, so I am assuming my success, so I'm denoting my success probability with P. Maybe I shouldn't have. This is 1 minus P, and let me erase this. And this is P, right? So because I just formulated my problem in that way, right? So this is 1 minus P, 1 minus P, because these are all failures, and my success is P. But so I'm denoting my success with P and my failure as 1 minus P, right? So because trials are independent, the probability of getting this particular sequence is going to be, I can multiply all these, right? 1 minus P, 1 minus P, 1 minus P. Sorry, this has to be 1 minus and P, right? So this is 1 minus P cubed and P squared, right? So this was for 5 times flip. Now we can generalize this idea in the sense that what if I had n trials, right? So let me generalize this. If I have n trials, or and I flip the coin n times, or any other trial with k successes, right? I can still have this kind of sequence laid out for me such that I'll have like these zeros, let's say n minus k times, right? And I'll have like all these ones, which is my success. I already said I have k successes, so k times, right? So I hope I have another slide that's blank. Okay, I don't have enough space. Let me write it here, and then I'll come back to what this definition tells us, but I'm continuing my example. So the probability of X success in, or maybe K, we said K, right? K success in N trials is given by P of K 1 minus P N minus K, right? Now, we assume that we are interested in k successes given n trials, and this formula above gives us one such sequence, right? This is just one possible sequence where I get all these set of n minus k failures and then k successes, right? But from our knowledge of counting, I know that a binomial coefficient can give me the number of all such strings that will have like k successes and n minus k failures, right? For example, for probability x, let's say going back to our x equals 5 or n equal 5 example, we can have all possible values where I'm getting 3 successes by using the binomial coefficient such that n choose 3 and then p cube 1 minus p n minus 3, right? So in general, for p x equals k, I can safely write n choose k p k 1 minus p n minus k, right? And so this is what my statement here for binomial distribution says. If x is the number of successes in n independent trials with success probability p, which we can either calculate or we know from the question itself, then x, which is the sum of all these, and obviously if you think about the tossing of a coin, I'm going to get ones for all the successes here, right? And the way we denote that each of these x's is a Bernoulli random variable, then the probability distribution function for the binomial random variable or the binomial distribution function is denoted like this, right? So notice the 3 parameters, right? Success, the number of trials, probability of success. So we need these 3 important parameters in order to compute the binomial random variable, or in order to compute the probability of the binomial random variable, or the probability distribution function for any given values of k, right? Okay, let's look at a quick example here. Here, a multiple choice test has 20 questions with 5 answers per question. You guess randomly. Compute the probability that you pass. For example, compute the probability that you get at least 50% of the total number of questions correct, right? So now every question that I'm trying is a Bernoulli trial with the chances of success 1 out of 5. Why? Because 5 answers per question, only one is correct, right? So, and I'm interested in getting a pass percentage, which is 50%. So I'm interested in getting at least 10 out of 20 correct, right? So this is easy to solve now because I can just substitute the values. All three parameters in this formula are known to me, right? So I know K is 10, N is 20, and P is 1 over 5, right? So just go and substitute all of them here and get the answer, right? So it's 20, choose 10, and then 1 over 5 is my P, right? And this is good because this is 10, and then 4 over 5 is my 1 minus P, and again 10, right? So this is an example that demonstrates the application of a binomial random variable, right? And then we also understood the relationship between Bernoulli and binomial. In the next video, we'll talk about the uniform random variable and the exponential.